Let's talk about random numbers. My latest videos, a couple of the last three videos, two of them were about an experiment with a true random number generator. And a comment came up where someone said, well, there's no such thing as truly random in the universe. So I'd like to talk a little bit about random number generators and a little bit about randomness. Um, for something to be truly random, it needs to uh, be statistically random. So, not like, so if you're generating ones and zeros, uh, there should be about as many in a some given period of time, there should be about as many ones as zeros generated. But there also should be other statistical properties about the numbers. Okay, so there is in existence a battery of tests that can be applied to a random number generator to see if you could call it statistically random. So that's one aspect. Another aspect, though, about true randomness is its predictability. So we just define truly random as statistically random and unpredictable, meaning we can't predict it. So to the comment that said there's no true randomness, well, we'll look at that a little bit later in here about, well, is there anything that is unpredictable by us? So let's start with the basics in computers that for so long we had and still do had pseudo random number generators. But way back, like when I started in computers, the pseudo random number generator that was popular was called DRAND 48, and unfortunately, it was predictable, meaning that because it was produced algorithmically, that it would start with a seed and then add values to get the next value and add to get the next value. Okay, so and then probably mess with the bits, but I actually don't know the details of DRAND 48, but it, of that class of pseudo random number generators, they're called because they're not truly random. Um, they're predictable. If you know the history of that particular random number generator, you could predict the next number. And so that was fine when we're doing games. You started off with a seed value, and then it would have the appearance of doing random things in the game, and that's sufficient. But once we started doing cryptography and being very dependent on cryptography, and where we need to generate keys and things randomly, that is no good anymore because if you could predict if you could if you could you would be able to short reduce your search space if you knew the random number generator used and its history. Okay, so we have now what's called cryptographic random number generators. Now those generators are pseudo random number generators that where you cannot predict. So if you see the history of it, you can't predict the future. You can't predict the next number. So and so, however that's done algorithmically, it's guaranteed that you can't, from its history, predict the next number. However, those also need to be seeded, and so if you knew the seed, then you could predict its output. But typically, with cryptographic random number generators, they don't. they don't use a predictable seed. They use some source of what we call entropy, an entropy source, such as a true random number generator, to generate the seed, and then it will do its algorithm to produce the subsequent random numbers, which are unpredictable. See, why not use a true random number generator to begin with? Well, it takes some doing to have one of these true random number generators, and they're typically slow. I mean, relatively slow to an algorithm, a pseudo random algorithm. Okay, so on typical computers, they use some noise sources to generate the so-called true random numbers that are used as the seeds for pseudo-random number generators. And they use, and so, you know, noise, if it's got the right distribution, or you can munge it into a good distribution, a random distribution, noise sources are okay to be called random. Okay, they pass the unpredictability test. Things such as like taking, you know, time between keystrokes, audio noise, voltage, noise in the A to D converter on an open microphone, thermal noise of some sort. So just picking up thermal noise. These can all be used to generate what they call entropy, which is just a measure of disorder. So, and so that's a way to have an unpredictable seed, because someone would have to, you know, monitor your environment, you know, where the machine is located to be able to predict those numbers, you know. So, but we have these other things now. So that's pseudo-random number, non-cryptographic, and then there's cryptographic pseudo-random numbers, and then there's true randomness. Now, true random number generators are hardware. They're done in electronic hardware that uses some source of unpredictable noise. Now, the ones that I'm interested in are using quantum mechanical events, such as, now, this is not happening inside of a computer, but they have built true random number generators based on nuclear decay, because we cannot predict, though we know stuff about the statistics of nuclear decay, we cannot predict when, you know, the time between the decay of particles, atoms. Okay, so that is unpredictable. And there's another quantum mechanical event of an electron tunneling. So an electron can quantum mechanically tunnel through a potential barrier occasionally under the right circumstances. And that event, those tunneling events are unpredictable. So, you know, it's as unpredictable as quantum mechanics is when we say that we can't predict this event. You know, so it may be, now if you look into this, there are people that say, oh, no, we're in a clockwork universe. So somewhere underlying quantum mechanics is the predictability, but we're just no good at doing the prediction. But this is not generally held. It's generally held that, yeah, we really can't predict these things. Now, so the kinds of true random number generators that I have used, I bought one. You can get it on Amazon. The one I bought on Amazon has 2 hardware random number generators in it, and they state that it uses reversed bias diodes. So when you send voltage backwards through a diode, electrons will randomly tunnel, and you'll get a signal out, and that'll be a noise signal. And from that signal, you can amplify it and get noise in the range that you need for your logic, and then it's thresholded into zeros and ones, and da 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 da. We get from a single bit of a 0 or a 1 into bytes of zeros and made up of zeros and ones. So I suspect now you could also do that with reverse biasing a transistor. So you can send voltage. You can attach take an NPN transistor and attach its emitter through a current limiting resistor to the plus voltage, and it will cause an electron tunneling effect, and then you can amplify that. And again, like a diode, you can get that as a noise source, which is unpredictable. So I suspect that since those 2 methods, the diodes and transistors, are based on silicon, that now this is where I'm making an assumption. So my videos were about the Cortex M4, which in the data sheet says, hey, we have a true random number generator. Well, then it's kind of like very simple for them to just have a reverse bias diode or transistor on the chip, and to do it that way. But I don't know for sure if that's the way they do it, because they could also be using some other form of environmental noise and calling it a true random number generator. So, once I kind of like got into this, like revived my interest in random number generators by coming across that Adafruit Itsy Bitsy M4 and saying, oh, it's got a true random number generator. Oh, I can make an experiment. Oh, I post it and I got a couple comments, and I go, hey, wait a minute. A few years ago, I was designing my own hardware random number generator based on a transistor, and I stopped my development of it when I realized I could just buy it on Amazon. But now I'm back to, hey, I'm going to have some fun, and maybe I'll make some videos about how to build one of these things for yourself. It will use inexpensive components, though I'm going to use a printed circuit board. You can get inexpensive. You can get your designs printed on printed circuit boards pretty inexpensively now. So there was something else. There was this other thing that I did recently with random numbers. I made for Christmas presents something that I might make a video for also, but I don't know. Not a lot of people look at my lengthy videos. I get a lot of views on the shorts, but I don't get a lot of views on the lengthy videos, probably because I don't know, ramble. But I made I took one of those 8x32 dot LED displays and hooked it up to an ESP32, and I programmed in quotes from the Bible in it, and what it does is randomly, at random times, scroll by a Bible quote. And I did it for my pastor, and then other people liked it, and I made 3 of them just as gifts. That's, the actual use of it is not the point here, but I needed random numbers. Okay, so using an ESP32, I was only, I think, and I was only going to get pseudo random numbers, and I would have to get a seed from somewhere. And uh, I was like, well, if I'm going to try to use noise to get a seed, I might as well use noise for the random numbers. And so because it's low bandwidth, I don't need random numbers maybe every 10 seconds. So what I did for that, I as a noise source, I used a floating input on an analog to digital converter. So I just took a pin and one of the ADC pins and programmed it as an ADC pin, and said, okay, start giving me values, though the pin is unconnected. Now that's going to give all kinds of noise, an unconnected pin. It's going to get, you know, basically electromagnetic interference. Everything is going to be hitting this pin, radio, because it's just floating. Radio waves and your house wiring is it will be picked up. Your 60 cycle hum of your house wiring will get picked up by that pin. And so it's just a general mess of noise plus thermal noise. And I used that, and it worked out great because it's not cryptographic. I don't need it for cryptography. I just needed it so that, it didn't play the same things, the same quotes out every time you rebooted the thing. So I used electrical noise, and it worked out well. So that's another way of getting I think it satisfies randomness, at least the unpredictability aspect. It was fairly uniform in as a distribution of numbers, but I did no statistical tests on it, and it didn't need to be, statistically random. It just had to appear random to people. I didn't have to pass statistics. So all this to say that, hey, maybe I'm gonna show you some a video in probably about a week's time of me working on building a true random number generator with a transistor. In that one, I'm going to try and use, they call them ATtiny 85s. It's a little 8-pin DIP package. It's a little AVR, 8-bit microcontroller. And my original design for this, my hardware random number generator, had the reverse bias transistor going to an amplifier, and then an op amp, and then from the op amp going to what you need is a Schmitt trigger to threshold, because it's going to be coming out an analog voltage. So using a Schmitt trigger to threshold it to get a 1 or a 0 out of it. Now that should have random characteristics, and I had read that you can improve that randomness by cascading multiple copies of the random number generator and XORing their outputs together. So basically, I designed a four generator thing going into some XORs to a pin on a microcontroller. Well, I was thinking about it today, and I was like, why did I do all that? Well, at the time, I wasn't very at ease with just putting a microcontroller chip on my boards. But, this ATtiny 85 is just so easy to work with. It doesn't need any external components. Sure, you could put a crystals on it to get to have a stable clock, but you don't need a stable clock for what I want to do, things I did with it. So it's very easy to put on a board. Now that thing has 4 analog to digital converter pins. Now, what I am thinking is I might be able to get away with, it depends on how much amplification I really need, because, and I don't know yet, how much amplification do I really need for the signal coming out of the base of the transistor. So if I don't need a lot of amplification, I might throw out the XOR and the op amp altogether and just go right into an ADC and use that as numerical noise. And with 3 of them, I can't use all 4 of the ADCs. I could use 3 of them. So with 3 of them ganged up, and I could sum together their noise and get a number out of that, a random number out of that. If I need amplification, I'll put the op amps in, but I still won't need the XORs or the Schmitt trigger, which was in the XOR, because I could just use the ADC, read the numbers, do the thresholding, and do the thresholding in software. The thresholding and XORing I can do in software. So that's a thought I have for my future. I might just have 3 transistors, some resistors, capacitors, and an A-Tiny 85 on a board, and a power supply, because the transistor needs more than 5 volts to do its magic. But let's see. I'm going to, get the transistors. I don't have any right now. And I'm going to start with transistors and whatever passive components I need, and just hook my oscilloscope up to that and see what really is coming out of this transistor setup as far as voltage range, to see if I need amplification or attenuation or whatever in order to feed to the ADC on the A-Tiny. I think I'm rambling, so I'll stop now.